How to design a bandgap reference diode circuit, how does it work, and what are the applications for this circuit? These are the questions that I discuss and answer in this video. Similar to the idea of Zener diodes, that there are many practical applications for it in terms of providing a fixed reference voltage, let's say between two terminals. This is exactly the idea behind the reference diode based on bandgap, which means that between these two terminals at this port, we will have a fixed voltage that I am going to compute, and I'm going to show you that actually turn out to be 1.28 volt roughly. Interesting. Now, what is the difference then? Why not just using Zener diode? Well, the problem is for Zener diode, for example, let's say 4.7 volt or whatever other voltage you consider, when you look at the data sheet of that is provided, you will see a specification which is referred to as temperature coefficient, which means the nominal voltage of Zener diode, as the temperature is changing, the nominal voltage is changing as well. How much? It can be as large as, say, plus minus 0.08 or 9 percentage or percent per degree C, per degree Kelvin of junction temperature of the Zener diode. So that can be considerable when you have considerable change in the temperature of the junction. Contrary to that, this voltage reference diode is designed in a way that this generated voltage across these two terminals as the voltage of diode is going to be with temperature coefficient nearly zero. So the expectation is over change in temperature of the junction of these, let's say NPN, or let's say these bipolar junction transistors or BJTs, the change in the value of 1.28 at the output will be very minimal. That's the idea then. Okay, so to see how this is possible, let's see how the circuit is working, and then I'm going to find and compute this 1.28 volt quickly. Okay, so let's see. There are 5 NPN BJT transistors. I'm going to name them, and 1 PNP. So T1, T2, transistor T3, T4, and then let's say transistor T5, which is our PNP transistor, and then finally the main output transistor, that is T6. What's happening, I'm going to show you that the combination of T1, T2, T3 will actually, with the R1, R2, and RE, these three resistors and transistors, will actually generate this voltage for us. And then what the T4 and T5 are doing, they are actually providing this float node that can support the base of transistor T6 that then can act as the main current bearing transistor for the current I, because the expectation is if you want such a thing like a Zener diode, similar to idea of Zener diode, then you want a fixed reference voltage at the output. For example, in this case, I am saying 1.28, but then you are expected to have a voltage that is not sensitive, at least for a reasonable range, sensitive to the current that is flowing. So you would specify a minimum current, like the bias current of a Zener diode. You would say we need at least this much of a current, but then as the current is changing, you don't expect the 4.7 volt change. The same idea here. This current should be at least a minimum amount, but then beyond that, we don't expect that it affects the 1.28. So when there is an increase in current, the main transistor that actually carry the current is this T6. Okay, so now that we know the big picture, let's go through the analysis of this circuit. So first, let's focus on transistor T1, and we know that we are saying, as is shown here. So let's say here we have plus minus between these two terminals. Similar to the output, we have plus minus V diode. Let's say the current that is going through R1 is I1, the current that is going through R2 is I2. So what I can write is, of course, this VD, or the voltage of diode. I'm just writing a KVL across the two rails. So rail 1, rail 2. I'm going to write a KVL across this branch. So if I do a KVL or Kirchhoff voltage, I would see that it says the total voltage VD is the voltage drop across resistor R1 plus this transistor that is in diode formation. So I'm going to have basically R1, I1. So that's the voltage drop across this guy, and then plus VBE1, the voltage of the base emitter of transistor 1, which is this voltage. Great. So, but what is the benefit of this? All right, so let's keep that, but then let's refer to this as equation 1 for now. So I am just referring to this as equation 1. I'm gonna extend that, but now look at what we have from the base of transistor T2 to lower rail. So we have in one, let's say on one side, we have just the base emitter of transistor T1. On the other side, similar to a Widlar current mirror, or let's say current source, we have the transistor T2 and the voltage drop across RE. So what I can say the voltage of base emitter of transistor 1, so this voltage, which means from here to here, given the diode formation, is equal to the voltage of base emitter of transistor 2, so VBE2, and minus RE. This current I2 keeps going down and it will go to the RE. So this is current, I'm going to just refer to it as current I2. So RE I2 plus. Now let's move VBE2 to the other side. So I'm going to have VBE1, and minus V base emitter 2 equal to RE I2. What I'm going to use now is I am going to use Shockley PN junction, the famous Shockley PN junction equation, which is the equation that governs the IV or current voltage relationship for the PN junction of a bipolar transistor, which says voltage of, let's say, base emitter is equal to the thermal voltage of junction, which is roughly at nominal temperature 26 millivolt, times natural log of the, let's say, emitter or collector current. So it doesn't matter which one we refer to, approximately divide by saturation current of transistor. So this is the well-known Shockley PN junction equation for bipolar transistor. All right, so we know that, so let's say this is equation 2. I'm going to delete this one for now, but that's our target. We know that VT or thermal voltage is KT over Q, in which case Boltzmann constant, T is the junction temperature in Kelvin for the, let's say, PN junction, and Q is the electron charge. So if we compute that at nominal temperature of, say, about 300 Kelvin, room temperature roughly, we end up having VT or thermal voltage to be roughly 26 millivolt. So that's our reference for now. But that is only when we are talking about room temperature. So, okay. IS is the saturation current of transistor that is heavily depending on temperature. So IS roughly proportional with temperature of the junction to the power 3. So cube, temperature cube. So it is very sensitive to temperature. We want to get rid of it, and that's exactly what is achieved by these two. So the reason that in this band gap reference we have these two branches is mainly just to get rid of the IS. That's exactly what we are doing. That is happening here. So let's substitute using equation 2. So using equation 2, I am going to substitute, and I get, instead of VBE1, I have VT natural log I1 divided by I saturation, and VT natural log I2 for VBE2, and the current I2 is passing through transistor, so it will be I2 over IS equal to RE I2. The reason I use the same IS for the two transistors that are T1 and T2 is because we make the assumption that transistors are matched. At least the assumption should be valid for, let's say, transistors T1, T2, and T3. So these transistors should be matched, which means they should be on the same substrate and having same PN junction process and thermal properties, and therefore they have the same IS. So the benefit of that is I can factor out the VT then. So there you go. I'm going to factor out VT. So VT outside, and then I have minus this, which I can therefore write it simply as VT ln. So IS cancel out, and then I have I1 over I2 equal to RE I2. Let's refer to this as equation number 3. All right, so what is the last step? To just find the output voltage for the diode voltage and showing that it is equal to roughly 1.28 fix. I'm going to write another KVL across R2 and then the base emitter of transistor T3, which basically from rail to rail, upper rail and lower rail, I can do exactly as I did before. KVL, I can say the total voltage drop across R2 and base emitter of transistor T3 is equal to R2 I2 plus the voltage of base emitter of transistor T3. Okay, so what I can do now here is I can just deal with the I2. So what I'm going to use is I am going to modify equation 3. So I can from equation, or basically I can just from equation 3 find the I2. So I2 is obviously 1 over RE and then VT ln I1 over I2. So I can just use that and substitute for I2 here. So I can say, okay, VD, the reference, the voltage of this supposed to be a diode, is R2, and then substituting for I2 from here, I can just say R2 over RE, the emitter resistor, and then times VT and ln I1 over I2 plus VBE 3. Okay, so this is the voltage of diode. Now, what did we achieve here? Let me just also expand this in this form. So I am going to say, therefore, the voltage of diode, or supposed to be the reference diode that we are constructing here, is R2 over RE, and then ln I1 over I2. So I got rid of IS, the heavy dependence on temperature cube, which is very large. So, and then for VT, I'm going to just substitute the well-known KT over Q. So it's a linear function of temperature. So K over Q T, the junction temperature, and then VBE 3, which is governed by equation 2 effectively, the Shockley p-n junction equation for VBE. Now, it is well known that, so let me just highlight this as equation 4, which is super important because that's actually the sort of one of the main outcomes in this study. So in equation 4, that's the voltage of diode, this diode, effectively what the voltage that is generated at the output of the circuit. I want that voltage not to change. Basically, I want the temperature coefficient be near 0. So what should I do? The change in that voltage as a function of temperature need to be set to 0. So let's compute that. The nice thing is when we are computing the, let's say, when we are computing the change in the voltage as a function of temperature, we take the derivative with respect to temperature. And as you can see, one of the nice things in this design is this. Take a look. So this component here that is multiplying the temperature, effectively, we can assume that this is not a function of temperature. Reason for that is, of course, K and Q, the Boltzmann constant and electron charge are fixed known constants, so we are okay about them. The I1 over I2 can be designed to be a fix that is not changing. It's a relative value, basically. If there is a change as a function of temperature or process, let's say, it affects in the design, given the matched transistors, it affects both of them. So I1 over I2 can be assumed to be pretty constant as a function of temperature. R2 over RE, the same thing. See, R2 is here, RE is here on two sides, on collector and emitter side of transistor T2. It can be designed, especially in integrated circuit inside a chip, or even, let's say, if you're using very close resistors, we can place them in a way that the ratio of these two resistors, whatever the change they have, let's say this one is changing with temperature increasing, let's say this one is changing with temperature increasing, we can design them in a way that whatever they change, observe, they experience the same rate. So therefore, the ratio of R2 over RE will be independent of temperature because they both change same amount percentage-wise. Therefore, the lesson is this component is not a function of temperature. So I'm going to just put it this way. This term is practically not a function of temperature. is just a constant temperature-wise. So therefore, when we compute the derivative of this whole thing as a function of temperature with respect to temperature, it's just a linear temperature here, and this constant just shows up here. So I'm going to have R2 over RE, and then natural log I1 over I2, and K over Q. So that's one benefit. If one thing I can do is, so that is for that component. I'm going to show you one step further, but then plus change of the base emitter voltage for transistor T3 as a function of temperature. This is a well-known value. It's well known that for a PN junction transistor, for a let's say BJT transistor, sorry for this one, for a BJT transistor like T3 plus minus VBE3, the base emitter voltage as a function of temperature is it has a temperature coefficient of roughly minus 2.1 millivolt per degree C or degree Kelvin. Doesn't matter which one. So this is well known. It's a property of the PN junction, let's say BJT transistor. So therefore, if I need to set this whole thing to 0, so setting this whole thing to 0, I get that this term, so R2 over RE ln I1 over I2, and K over Q, I can add a T, I can drop a T. So just add a T in numerator, drop a T, and also add a T in denominator. What's the benefit? Well, this thing is VT. So I am going to just write VT over temperature is equal to, and then plus this component is 0, which the component is minus 2.1 millivolt per degree Kelvin. I can move it to the other side. So 2.1, let's say, millivolt per degree C or Kelvin. That's it. That's a very nice outcome that I wanted to get. So what is the benefit of this? See in the previous equation what we had. So as soon as I find this, let's just refer to this as equation, let's say 5. As soon as I have this, then what I can do is I can go back to, say, equation 4, and I can substitute, because now I found actually what is, I found, so maybe one step further so that I can, so let's refer to this as, do one step further. I'm gonna move this T to the other side, and I'm going to use the nominal room temperature for the junction temperature. So if I say we are doing room temperature of roughly 300 Kelvin, which correspond to about 27 degrees C for the PN junction temperature of BJT transistor, I can say R2 over RE natural log I1 over I2 VT is equal to 2.1 times, that's millivolt per Kelvin, times T, and T is 300 Kelvin for the nominal room temperature, which means this whole thing in this design will be equal to 630 millivolt. That's interesting. So what we found is exactly this component, right? This component in the VD equation. And that is what I needed. So I'm going to go back to equation 4, and I'm going to substitute for this whole thing as 630 millivolt. So using equation 4 and 5, I can say then the voltage of the resulting voltage of, let's say, reference diode is equal to then 630 millivolt plus V base emitter of transistor 3. And remember, we are dealing with the reference point of room temperature. At room temperature, voltage of base emitter of transistor T3 is nominal 650 millivolt, about 0.65 volt. So it is 1280 millivolt which is exactly as I said. So the voltage of reference diode is 1.28 volt on that ballpark. Remember that the design is in such a way that as temperature is changing, they're compensating each other. So all I'm trying to say is this 1.28 volt is a valid constant voltage because when you change the temperature, one component, which is this one, will go down and this component will go up. So they counteract exactly each other because we intentionally set this value here, this coefficient here, using the selection of R2, RE, and I1 and I2 to exactly counteract the reduction of base emitter voltage of transistor T3. So this is the resulting reference diode voltage based on band gap. And band gap refers to this structure basically. So band gap meaning that a voltage reference that is we are using the band gap property of, let's say, PN junction. And as a result of that, in this structure, we generate a voltage at the output that is independent of temperature, practically speaking. And the value is 1.28. So I prove that effectively as if we have a perfect Zener diode with a voltage of 1.28. That's exactly what we did. Now, as I said, the main current, let's say, bearing transistor is T6. So we can now design components as a part of making sure that just minimal amount of current as bias current is passing through this element. So for example, let's say, just as an example, you can do it with other values you would like. I can set I1 equal to, say, 0.5 milliamp or 1 milliamp, doesn't matter. So let's say 1 milliamp, and let's make the assumption that the HFE or the current gain beta of these transistors, which is IC over IB, the current of the collector with respect to or divided by current of base, let's make the assumption that's reasonably large given that these transistors are, let's say, small current transistors. So we are talking about on the order of 200 or larger. The reason I mention that because I just want to make sure that we understand in our consideration, we are neglecting the base current of the next stage transistor when we are dealing with the, let's say, KVL that I wrote. So that's a reasonable assumption because the base current for these transistors will be considerably small compared to the branch current. And these HFE or beta assumption that are practically valid assumption are going to help us. Okay, so let's see what's going on then for the selection of component. As I said, I'm done with proving that we get 1.28 volt at the output of the circuit. I just want to give you an example of how we select the value of R1, R2, R3, and RE in this circuit. Let's say we select I1 to be 1 milliamp. You can select it to be 0.5 milliamp. It's just an example here. Let's say I3 here in this branch also selected to be same as I1. So I3 equal to I1, 1 milliamp, for example. And so I'm going to make these assumptions here to just quickly compute one practical implementation example. So I1 equal to I3 equal to, say, 1 milliamp. And I'm going to make the assumption that, let's say, since in equation, as you can see, I am dealing with I1 over I2 as the argument of, let's say, log or natural log, I'm going to select I1 over I2 equal to, let's say, e to the power 1.5, because that would nicely get outside the natural log. So that is roughly 4.5 ratio. So basically, what I'm assuming is the current I1 going through R1 and the current I3 going to R3 are going to be equal to each other and about 4.5 times the current I2. That's what I'm making the assumption. Makes sense because this is a VDLAR structure with the resistor at the emitter of transistor T2. We expect that this branch has considerably less current than, let's say, a branch that has a transistor that without any resistor in the emitter. So it's basically just an emitter follower. Or common emitter. So okay, so let's see what's going on with this. I am going to apply it. Let's go back to equations we have. So immediately we can find from equation 3 RE. So that's exactly what I'm going to do. I'm going to use equation 3. Using equation 3, what I get is VTs in equation 3. The thermal voltage at the nominal PN junction at room temperature 300 Kelvin is roughly 26 millivolt. That's for VT. And ln, so we have ln I1 over I2. So that's now the nice thing we get because we have ln. And as I said, the selection is I1 over I2 is e to the power 1.5. So we get e to the power 1.5 equal to RE. And then I2, well, I just said that select I1, I3, both 1 milliamp, and I2 ratio with respect to I1 is 4.5 times smaller. So it's going to be 1 milliamp, which is I1, divided by 4.5. So, and this one is 1.5. So if we compute this, we get roughly RE 175 ohm, which is a reasonable, very reasonable resistor size, especially if you are doing, let's say, chip design or integrated circuit. That size of a resistor is a very reasonable resistor here. It's not too small, it's not too large. Now, let's say we want to find the rest of them as well. So which equation we can do? We can use, for example, what I can do is I can go ahead and use combination of R2, I2, and the base emitter of transistor T3, which is effectively this equation. So I am going to use that because VD is known now. I computed VD, which is the famous, let's say, final result I found for the voltage here, right? 1.28 volt. I'm going to highlight it with a red color. That is the voltage of reference diode we actually designed here. So what I'm going to do is I'm going to say, hey, VD equal to R2 I2 that we just computed plus VBE3. Basically, I'm repeating the equation that I'm showing here that I did before. So let's substitute for VD equal to 1.28 volt that we prove is a fixed voltage we are generating using this circuit. And then VBE3, which is the voltage of base emitter of transistor T3 at the nominal room temperature junction, is 650 millivolt, about 0.65 volt. So let's just substitute, and I2 is the one that I just computed. I just said is equal to 1 milliamp divided by 4.5. So let's just do that. We get 1.28 volt is equal to R2 times I2 is 1 milliamp divided by 4.5, because as I just mentioned, and then plus 650 millivolt. So as a result, I get R2 roughly on the order of 2.85 kilo ohm, on that order. So it's again a reasonable size resistor. It's not very large, and it's a reasonable size that we can actually design even in chip design. Okay, so that's R2. What about the last one, which is, let's say, the R1? Same idea. So what we can do is we can actually have it again across this branch. Basically, it means using equation 1. So I'm going to use equation 1 to find R1. So using equation 1, I have VD, same as what I wrote here. I have VD equal to R1 I1 plus this time voltage of base emitter of transistor 1, as you can see. So R1 I1 plus the VBE1 equal to the total voltage VD. And for that, using again VD 1.28, we get 1.28 equal to R1. The current I1 is assumed to be 1 milliamp in this example. You could have selected to be 0.5 milliamp. So 1 milliamp plus nominal voltage of base emitter is 650 millivolt. And then when we compute this, we end up finding R1 to be 600, let's say roughly 30 ohm. Again, a reasonable sized resistor that can easily be implemented So we found R1, R2, RE for this circuit. Of course, the R3 selection can also be easily done because it's going to be equal to the voltage of emitter base of this PNP transistor. So we're going to keep it on. That's the VEB of transistor 5, which is our PNP transistor. So what I can say is, I can say R3 I3 is equal to, let's say, nominal voltage. So it's going to be VEB, that's the PNP transistor, VEB of transistor 5. And again, nominal voltage for that is roughly 650 millivolt. Again, our reference is at, let's say, reference junction at room temperature, because we know circuit will compensate for any adjustment in temperature. So therefore, we have R3 is unknown, but I3, as we assume to be equal to I1, so it's going to be 1 milliamp, and it's going to be 650 millivolt for the other one. So what we found is just R3 is 650 ohm. In some of the variants of this design inside the chip, instead of having R3, there will be current mirrors actually. So there will be current mirrors that use these branches to actually have, let's say, PNP transistors on top that act like a current mirror to inject the current toward T3 to bias T3 and also provide, let's say, reference base voltage for T5. In this case, I am simplifying the circuit so that there is just the R3 here. Now, what is the benefit of these two guys? As I said, the benefit is making sure that the base of transistor T6 is at the proper voltage and also float enough so that whatever current passing through T6, that then through the, let's say, Shockley PN junction transistor, when current is passing through the collector or emitter of transistor, then it will set the base emitter voltage. So since the base of T6 is connected to a collector, it gives the T6 degree of freedom to have a slightly varying base emitter transistor, base emitter of PN junction, let's say, so that when different currents are passing through this transistor, there are going to be no problem for the current, for the voltage and current. Okay, I hope that this example is helpful in terms of showing what is the use case of a bandgap reference diode, how it is working, what are the rules of different transistors in the circuit, and what are the requirements, and then one example of selecting the components in the circuit as I showed you for a practical design. Effectively, we end up, as I said, with a similar to a Zener diode. We end up with a fixed voltage of 1.28. And we are saying if, for example, in this sample implementation, we select 1 milliamp, and we ended up with 1 over 4.5, something like, let's say, 200 microamp for I2. And on that same order for, let's say, the current of transistor T5. So effectively, I would say the minimum current requirement for the bias of this reference diode would be about 2.5 or 3 milliamp. So as long as we have, in this example that I implemented, as long as we have, say, 2.5 milliamp or higher, the circuit is biased and it will work. And of course, there will be some maximum current that is basically depending on how much max current this transistor can carry. That should be defined for this reference, let's say, diode. I hope this is helpful. Thanks for watching.